Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Google Introduction to Agents and Agent Architectures. For years, most AI systems have been like very smart calculators. You give them a prompt, they give you an answer, and then they're done. They don't remember, they don't plan, and they don't act on their own. This paper describes a shift to something more powerful: autonomous agents. An agent isn't just a language model in a box. It's a full application that can understand a goal, break it into steps, call tools and APIs, and keep going until the job is done. In other words, agents are language models made truly useful in software. An AI agent is best thought of as a loop, not a single model call. The loop uses a language model repeatedly, along with tools and memory, to move toward a goal. Architecturally, every agent has four pillars. First, the model, which is the reasoning engine. Second, tools, which let it read and change the outside world. Third, an orchestration layer, which decides when to think, when to act, and how to manage memory. And finally, deployment, which turns the agent into a reliable, observable service. At its core, an agent is a system for curating the model's context window so that each step has exactly the information it needs. Building an agent is very different from writing a traditional program. Instead of hard-coding every logical step, you act more like a director. You define the agent's role and personality, choose which tools it can use, and decide what context it should see. The language model fills in the details. But that flexibility comes with a cost. It's harder to make the system behave exactly as you want. That's where Agent Ops comes in. By tracing the agent's reasoning, tool calls, and outcomes, you can measure performance, debug failures, and iteratively refine prompts, tools, and policies until the system is reliable. Under the hood, most agents follow the same basic loop. First, they get the mission, a high-level goal from a user or a trigger. Second, they scan the scene, pulling in relevant context from memory, tools, and a current request. Third, they think it through, using the model to plan a sequence of steps. Fourth, they take action by calling tools, APIs, or code. Finally, they observe and iterate, folding the results back into context and deciding what to do next. This think, act, observe cycle repeats until the mission is complete. To make this concrete, imagine a customer asks, "Where is my order 12345?" A naive system might just hit a single API and reply. An agent does more. It first plans. It needs to confirm the order exists, get the tracking number, then query the shipping carrier. In its first action, it calls a find order tool and observes the full order record, including the tracking ID. Next, it calls a get shipping status tool and observes that the package is out for delivery. Finally, it synthesizes everything into a clear response. The key is that the agent isn't just reacting, it's reasoning about a multi-step plan and executing it. Not all agents are created equal. This paper lays out a simple taxonomy of agentic systems. At level 0, you just have a language model answering questions from its training data. At level 1, the model can call tools and access live information. Level 2 adds strategic planning and careful context management, so the agent can handle more complex, multi-step tasks. Level 3 moves to a team of specialists model, where multiple agents collaborate. And Level 4 is the frontier, systems that can create new tools or even new agents to extend their own capabilities. Level 0 is the pure language model. It has no tools, no memory, and no access to your live systems. It can explain concepts, reason through hypothetical plans, and answer questions about what it has seen during training. But it can't tell you last night's sports scores or the status of a current order, because those facts simply aren't in its weights. This level is useful for many tasks, but it's not yet an agent in the full sense. At level 1, the model becomes a true agent by gaining hands, tools. It can call a search API, query a database, or use a RAG system to look up internal documents. Now, when you ask for last night's game score or a live stock price, it recognizes that it needs fresh data, calls the right tool, and incorporates the result into its answer. This is the foundation of grounded, factual behavior, but the tasks are still relatively simple and reactive. Level 2 is where agents become strategic. They don't just call a tool once, they plan a sequence of steps and manage context carefully along the way. For example, to find a good coffee shop halfway between two offices, the agent first calls a maps tool to find the midpoint, then uses that result to construct a focused search query for highly rated coffee shops nearby. At each step, it decides what information to carry forward and and what to ignore. This context engineering is critical for accuracy, efficiency, and cost. At level 3, the architecture starts to look like a company. Instead of one giant agent trying to do everything, you have a project manager agent that delegates work to specialists. For a product launch, it might assign market research to one agent, press release drafting to another, and web page generation to a third. Each agent has its own tools, prompts, and responsibilities. The project manager coordinates them, just like a human leader would. This pattern is powerful for automating complex cross-functional workflows. Level 4 is the most ambitious vision in this taxonomy. Here, agents don't just use a fixed toolbox, they can expand it. Suppose the project manager agent realizes it needs social media sentiment tracking, but no such tool exists. Instead of failing, it calls a higher-level agent creator tool with a mission. Build a sentiment analysis agent that monitors specific keywords and reports daily. Once created and tested, that new agent joins the team. Over time, the system can grow its own capabilities, becoming a self-evolving organization. To actually build an agent, you need to design 3 core components. The model is the brain, responsible for reasoning and decision-making. Tools are the hands, letting the agent retrieve information and take actions. And the orchestration layer is the nervous system that connects them, running the think, act, observe loop, managing state and enforcing policies. The rest of the paper dives into how to choose and design each of these pieces for real-world systems. Model selection is one of the most important design choices, but it's easy to get wrong. The best model on academic benchmarks isn't always the best for your product. Instead, you should test models directly on your use case, your code base, your documents, your workflows. Then balance 3 factors: quality, latency, and cost. Often, the right answer is a team of models. A powerful frontier model handles complex planning and reasoning, while a smaller, cheaper model handles high-volume tasks like classification or summarization. Routing between models intelligently can dramatically improve both performance and economics. Agents increasingly need to work with more than just text. You have 2 main options. One is to use a natively multimodal model that can directly process images, audio, and text in a unified way. The other is to use specialized tools like a Vision API or speech-to-text to convert the world into text, and then feed that into a language-only model. The first approach is simpler to wire up. The second gives you more flexibility and best-of-breed components, but it also adds complexity to your orchestration logic. The model you choose today will almost certainly be outdated in 6 months. That's why you need an agent ops practice, not a one-time integration. Think of it like CI/CD for models and prompts. You continuously evaluate new models against your real business metrics such as task success rate, time to resolution, or error rate. With good observability and automated tests, you can safely upgrade the agent's brain without rewriting the whole system, keeping your application at the frontier of capability. Tools are what turn a smart chatbot into a useful agent. Each tool needs a clear contract that defines what it does, how to call it, and what it returns. The agent then decides when to invoke a tool and how to interpret the result. Common tool types include retrieval systems for grounding answers in documents or databases, APIs for interacting with business systems, code execution for dynamic computation, and human-in-the-loop tools that pause the workflow and ask a person for input or approval. Together, these tools let the agent read and change the world safely. One of the most important tool categories is retrieval. Retrieval Augmented Generation, or RAG, gives the agent a way to look things up before it speaks. It might query a vector database of internal documents, a knowledge graph, or a web search API. For structured data, natural language to SQL tools let the agent turn a question into a database query, run it, and then explain the result. By grounding its answers in retrieved facts, the agent dramatically reduces hallucinations and becomes much more trustworthy for enterprise use. Retrieval is only half the story. The real power of agents appears when they can act. By wrapping your existing APIs and code as tools, you let the agent send emails, schedule meetings, update CRM records, or kick off workflows in systems like ServiceNow. For more complex logic, the agent can even write and execute code in a sandbox, for example, generating a SQL query or a Python script to perform a calculation. With the right safeguards, this turns the agent into an autonomous operator, not just an advisor. Not every decision should be fully automated. Human-in-the-loop tools let agents pause and ask for help. For example, before issuing a refund above a certain amount, the agent might call an Ask For Confirmation tool that sends a message to a human approver, or it might request a missing date or document from the user. These interactions can be implemented through a web UI, SMS, or task queues. Treating humans as tools in the orchestration layer keeps people in control where it matters most, while still benefiting from automation. For an agent to use tools reliably, it needs structured contracts. Standards like OpenAPI describe each tool's purpose, parameters, and response format. The model can then generate a function call that matches this schema and parse the result. Newer standards like the Model Context Protocol make it easier to discover and connect tools. Some models also have native tools, like built-in search, where the function call happens inside the model itself. The orchestration layer wraps all of this in security and policy checks, so the agent only calls what it's allowed to call with safe arguments. If the model is the brain and tools are the hands, the orchestration layer is the nervous system. It decides when to ask the model to think, which tool to call next, and how to update the agent's state. It encodes your business logic, safety rules, and reasoning strategies like chain of thought or ReACT. This layer is not just glue code. It's where you shape the agent's behavior, control its autonomy, and make sure it behaves predictably in production. One of your first orchestration decisions is how autonomous the agent should be. On one end of the spectrum, you have deterministic workflows that occasionally call a language model for a specific task, like classification or summarization. On the other end, you let the model plan and execute multi-step workflows with only high-level guidance. You also need to choose your implementation style. No-code builders are great for quickly automating structured tasks and empowering non-engineers. Code-first frameworks, like Google's Agent Development Kit, give engineers deep control, custom integrations, and fine-grained policies for mission-critical systems. A production-grade orchestration framework needs three things. It must be open and pluggable, so you can swap models and tools without rewriting everything. It must support hybrid control, where the non-deterministic reasoning of the model is constrained by hard-coded business rules. And it must be highly observable. Since you can't set a breakpoint inside the model's head, you rely on traces and logs that show prompts, intermediate thoughts, tool calls, parameters, and results. This visibility is essential for debugging, compliance, and continuous improvement. Within your orchestration framework, the most powerful lever you have is the agent's core instructions, often called the system prompt. This is effectively the agent's constitution. Here you define its role, like a customer support agent for a specific company, its tone of voice, its constraints, and when it should use which tools. Including a few realistic examples and edge cases is extremely effective. Well-crafted instructions turn a generic model into a domain expert that behaves consistently with your brand and policies. Agents feel intelligent largely because of how they handle memory. Short-term memory is the active scratchpad, the current conversation, recent actions, and observations. It's often represented as state, sessions, or threads. Long-term memory is usually implemented as a retrieval tool over a vector database or search index. It lets the agent recall a user's preferences or past tasks from weeks ago. The orchestrator decides what to pull from these stores and place into the model's context window at each step, balancing relevance against the limited size of that window. Building an agent on a laptop is a great way to prototype, but it's not enough for production. Deployment means hosting the agent on secure, scalable infrastructure, exposing it through APIs or UIs, and integrating it with monitoring, logging, and governance. As you move from one agent to many, agent ops becomes a discipline. You manage versions, roll out changes safely, enforce security policies, and ensure consistent behavior across a fleet of agents that may be talking to each other as well as to users. Because agents can take actions, not just answer questions, security is critical. You need to think in terms of blast radius. What's the worst thing this agent could do if it misbehaves or is misused? Tools and data access should follow least privilege principles, with fine-grained permissions and strong authentication. You also need continuous monitoring to detect unusual behavior, policy violations, or model drift. Security for agents is not an afterthought. It's a core part of the design. Multi-agent systems are especially useful for compliance-heavy domains. You can create dedicated policy or compliance agents that review the plans and actions of other agents. For example, before a customer support agent issues a refund or sends a sensitive email, a compliance agent can check the request against guidelines, either approve, modify, or block it. This pattern gives you both powerful automation and a clear, auditable trail of decisions. Beyond business workflows, agents can act as co-scientists or co-developers. In these setups, multiple agents take on roles like hypothesis generation, experiment design, result analysis, and critique. They iterate on designs, propose alternatives, and refine solutions over time. Humans stay in the loop to guide direction and validate results, but much of the exploration and iteration can be automated. This opens up new ways to accelerate research and engineering. A recurring pattern in advanced agentic systems is iterative refinement. An agent proposes a solution, tests it, observes the outcome, and then refines its approach. Over time, this can extend beyond single tasks to the system itself. Agents can suggest better prompts, new tools, or improved algorithms. With the right safeguards and evaluation loops, you get systems that don't just solve problems, but also help improve how they solve them. This is a step towards self-improving AI, always under human oversight. To wrap up, this paper frames agents as the next evolution of software, language models embedded in systems that can reason, act, and learn within guardrails. Building them well means thinking beyond prompts. You design the model mix, the toolset, the orchestration logic, the memory strategy, and the operational practices around them. With careful attention to security, observability, and evaluation, you can move from simple prototypes to robust, production-grade agentic systems that truly extend what your organization can do.